Welcome to today's presentation. All substances are made of atoms. These atoms have electrons, which are tiny negatively charged particles orbiting around the outside. At the center of the atom, there's a nucleus, which is incredibly small but densely packed. The nucleus contains protons, which are positively charged, and neutrons, which have no charge. Interestingly, atoms are mostly empty space. Most of what makes up an atom is just that empty space. Now, in some types of atoms, the nucleus isn't stable. Instead, it will spontaneously break down or decay into a more stable form. This process is called radioactive decay, and what's fascinating is that it happens completely on its own. It's spontaneous. When this decay occurs, the nucleus releases energy in the form of radiation. This phenomenon is the basis of radioactivity, which is what we're exploring in this presentation. Understanding how atoms can decay and emit energy helps us grasp a lot about both natural processes and their applications in science and medicine. Radioactivity, what is it? So, let's start by understanding what radioactivity actually means. Radioactivity refers to the process by which unstable atoms, or isotopes, emit radiation as they decay. This emission can be in the form of alpha particles, beta particles, or gamma rays, each with different properties and implications. It's a fundamental concept because it helps us understand how radioactive materials behave over time. Most importantly, radioactivity is a natural phenomenon, but it also has many important applications, from medical treatments to energy generation. In the context of our overall presentation, grasping radioactivity is key to understanding how we measure and utilize radioactive materials safely and effectively. Today, I want to talk about radioactivity, specifically alpha particles. Alpha particles are a type of radiation emitted during certain radioactive decay processes. They consist of 2 protons and 2 neutrons, which means they are essentially helium nuclei. Because of their composition, alpha particles carry a positive charge. One of the key points to remember is that alpha particles have relatively low penetration power. They can be stopped quite easily by a sheet of paper or even the outer layer of human skin. However, despite their low ability to penetrate, they can be very harmful if ingested or inhaled because they deposit a lot of energy in a very small area. Understanding alpha particles is crucial because they play a significant role in the overall behavior of radioactive materials. They help us understand how certain isotopes decay and how radiation interacts with matter, an important piece of the bigger picture in nuclear physics and health safety. So, as we explore radioactivity further, keep in mind that alpha particles, while limited in penetration, are highly energetic and potentially dangerous inside the body. This highlights the importance of proper handling and safety protocols when dealing with radioactive substances. Let's talk about radioactivity, focusing specifically on beta particles. Beta particles are a type of radiation emitted during radioactive decay. When an unstable nucleus undergoes decay, it can release a beta particle, which is essentially a high-energy electron or positron. These particles are quite interesting because they can penetrate matter more deeply than alpha particles, but they are less penetrating than gamma rays. Understanding beta particles is crucial because they play a significant role in both natural decay processes and various applications, such as medical imaging and treatments. They also help us understand the stability of atomic nuclei and how elements transform over time. So, as we explore this part of radioactivity, keep in mind that beta particles are a key component in the overall picture of nuclear decay and its practical uses. Today, I want to talk about radioactivity, specifically focusing on gamma waves. Gamma waves are a fascinating aspect of radioactive decay because they represent a form of electromagnetic radiation with extremely high energy. Unlike alpha or beta particles, gamma waves are pure energy and have no mass or charge, which makes them highly penetrating. This is why they're capable of passing through many materials, including human tissue, which has important implications for both medical treatments and safety precautions. Gamma radiation is often emitted when an unstable nucleus releases excess energy to reach a more stable state after radioactive decay. Understanding gamma waves is crucial because they play a significant role in how we detect, measure, and protect ourselves from radioactivity. In the context of our overall theme, gamma rays highlight the powerful and sometimes hazardous nature of radioactive phenomena, reminding us of both the potential for energy applications and the importance of safety measures. Let's take a moment to review the key points from this summary on radioactivity. First, we see that radioactivity involves the spontaneous emission of particles or energy from unstable atomic nuclei. This process is fundamental to understanding nuclear physics and has many practical applications and implications. It's important to highlight that radioactivity is a natural phenomenon, but it also has both beneficial uses, like in medical imaging and energy production, and potential risks, such as radiation exposure. Connecting this to the overall theme of our presentation, understanding radioactivity helps us appreciate how nuclear processes influence our world, from energy generation to medical advancements, all while emphasizing the importance of safety and responsible management. So, in essence, grasping these core concepts about radioactivity lays the foundation for more advanced discussions and informed decision-making in related fields. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the properties of alpha rays. Alpha particles carry a positive charge, which is essentially the same as that of a proton, and it's equal to the charge of a helium nucleus. Because of this, they are heavily charged, which influences how they interact with other materials. Their mass is approximately 4 times that of a hydrogen atom, so you can think of it as being roughly the same as the mass of a helium nucleus. This significant mass means that alpha particles are deflected when they pass through electric and magnetic fields, although not as easily as lighter particles like electrons. The velocity of alpha particles varies depending on the source emitting them, generally ranging from about 1.4 times 10 to the 7th meters per second up to 2.1 times 10 to the 7th meters per second. Now, because of their large mass, alpha particles have quite low penetrating power compared to other forms of radiation, such as beta or gamma rays. However, they are incredibly ionizing. They can produce thousands of ions before they are absorbed, which makes them very effective at ionizing materials in their path. The range of alpha particles in air depends on the specific radioactive source that produces them. Some sources produce alpha particles that can travel only a few centimeters, while others might travel a bit further. Interestingly, alpha particles can cause certain substances to fluoresce, like barium platinocyanide and zinc sulfide, which is a useful property in detection techniques. Finally, when alpha particles pass through thin metal foils, they tend to scatter. This scattering behavior is fundamental in understanding atomic structure and was key in historical experiments, like Rutherford's gold foil experiment. So all these properties, charge, mass, velocity, ionizing power, and scattering, are essential in understanding how alpha particles behave and their role in nuclear physics. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's talk about beta rays. These are high-energy, high-speed electrons or positrons that are emitted by certain fission fragments or radioactive nuclei. Basically, when a nucleus undergoes beta decay, it produces these particles. Now, beta particles are a form of ionizing radiation, and they're also known as beta rays. There are 2 types of beta decay. Electron decay, which involves negatively charged particles called negatrons, and positron decay, which produces positively charged particles called positrons. Now, regarding their properties, beta particles carry a negative charge of 1.6 times 10 to the minus 19 coulombs, which is exactly the charge of an electron. Their mass is very small, about 9.1 times 10 to the minus 31 kilograms, similar to that of an electron. They travel at speeds ranging from about 33% up to 99% of the speed of light, which makes them quite penetrating. Because of their small mass, they can penetrate further than alpha particles. They do ionize gases they pass through, but their ionizing power is only about 1/100th that of alpha particles. Another interesting point is that beta particles can produce fluorescence, which is useful in detection methods. And because they are negatively charged, they are deflected by electric and magnetic fields. This is a key way to identify them. So overall, beta rays are fast, penetrating particles with distinct properties that help us understand their behavior in nuclear reactions and radiation detection. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's talk about particle emission. When a particle is emitted, it doesn't change the atomic mass of the atom, but it does alter the atomic number. This process effectively transforms the atom into a different element with the next higher atomic number. So the mass remains the same, but the element changes. Now, regarding positrons, they are a type of antimatter particle. However, they are very short-lived, which means they don't have much practical use in biological applications. Their fleeting existence makes them less useful in that field. Moving on to gamma rays, these are a bit different. They are electromagnetic waves, meaning they have no mass and no charge. They are produced during the disintegration of radioactive materials. Some key properties of gamma rays include their extremely short wavelength and high frequency, which makes them highly energetic. They travel at the speed of light, and unlike alpha or beta particles, they are not charged. This means they are not deflected by electric or magnetic fields. Gamma rays can produce fluorescence when they hit photographic plates, which is useful in detection. They also ionize gases, but the amount of ionization is very small compared to alpha or beta rays, making them less ionizing overall. One of their most important characteristics is their high penetrating power. They can pass through many materials that stop alpha or beta particles. Because of this, they are difficult to shield and require dense materials for protection. Finally, gamma rays behave similarly to X-rays in some ways. They can be diffracted by crystals. This property is fundamental in techniques like X-ray crystallography, which helps us understand molecular structures. In the context of our overall discussion, understanding gamma rays' properties highlights their significance in fields such as medical imaging, radiation therapy, and scientific research, where their penetrating ability and high energy are invaluable. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide.